This is the setup for the electrolysis of a nickel, a 5-cent coin. So I've got my materials, 5-cent coin, lid for my 250 ml beaker. This is just a cardboard lid with a couple of holes punched in it. Graphite rod, 6-volt battery, some 6 molar HCl, voltmeter with appropriate wires. That's the materials needed. So the lid is used in the following way. Graphite post can be pushed through one of the holes, and you want the post to reach the bottom of the beaker, and there's a little bit left on the top. This is where we're going to make the electrical connection. So there's the graphite post in the beaker. The other side is going to be where the nickel is connected, so I'm going to pass the cord through the other hole, and it takes a little doing. So there I've got the cord on the other side. Clip that onto the coin. Clipping just the edge of the coin, that's the ideal. Clip the edge of the coin. Sometimes a little tape will help so that you can keep the electrodes on opposite sides of the beaker. So I'm going to put a little tape here on the cardboard. That looks pretty good to me. Now I'm adding the acid. My instructions call for 25 milliliters of 6 molar acid. Volume isn't really critical, but the suggestion is that the depth will be about 1 centimeter. And 1 centimeter is about halfway up your coin, so that if I put the electrodes in the beaker, the coin is half submerged. The half that's submerged sometimes does get a lot cleaner than it started, so sometimes students will notice that. But there's no real reaction other than a little shining up of the coin. So here you can see the bottom half of the coin is shinier, and that gives you an idea of the depth of the acid that is required for the reaction. Now I'm going to look at the electrical connections. This is the simplest setup I can do with a measurement in there, is to go from the negative to the negative pole of the ammeter. And now I'm using a green clip to take the positive pole of the ammeter over to the graphite post. And here's the red cord that's attached to the coin going back to the positive pole of the battery. So there's an incomplete circuit because I don't have an electrolyte solution. But that is going to create a reaction in the beaker. So now I'm immersing my electrodes, and I'm going to look at the current that I get on the ammeter. 1 amp is great. Above that, maybe less desirable. So here I've got about an amp on the ammeter. It's certainly not a constant current, but it's a decent current there. I have sometimes used a resistor in the circuit if I need to cut down the current, and I'll demonstrate that shortly. But here we have bubbles on the graphite. There's a little bit of color appearing in the solution from the coin. I'll give you a close-up now. So here's a close-up. You can see bubbles on the graphite. Green color appearing in the solution. This is how it looks initially. The bubbles are hydrogen gas. Here I have added a resistor to the circuit between the coin and the battery. So now I have an additional 3 ohms of resistance in the circuit. You can see that's dropped my current to a little less than an amp, which may be desirable. The higher the current, the more heat is generated in the reaction beaker, and as it gets hot, the acid does vaporize more, creating more dangerous fumes.
And so it may be desirable to decrease your current this way. That depends probably on the age of your batteries. When I've used brand new batteries, I have included the resistor because otherwise the current gets up around 2 amps, and that's really too high for this reaction. So now about 15 minutes or so have gone by, 10 to 15 minutes. You can see the solution is definitely greener than it used to be. The coin is black on the lower half, and we've got a nice solid buildup all around the graphite post. So I would let this reaction run longer, but these are the key features of the reaction that allow identification of products. Alright, so I'm disconnecting the electrical. That stops the reaction in the beaker. And as I lift this out carefully, here you can see the coin is discolored. The graphite has growth of copper metal on it. The solution is mostly green from nickel ions that have come out of the coin. The copper ions that come out of the coin actually come out as copper 1, which forms a complex in solution with the chloride ions and migrates as a colorless ion. So the color here will change upon standing due to oxidation of the copper 1 to copper 2, which has a much more robust color. At this point I can collect the solid through decanting the liquid, so I'll try to do that and wash it up a little bit. So here's the liquid I decanted. I'm doing a distilled water rinse of the copper metal. As I pour the water into the electrolyte, you can see that there's a color change, and we're diluting the chloride ions. So the nickel complex with chloride is greener, and as that chloride gets diluted, then we get a more aqua tinge of the nickel ions in aqueous solution. So this is the copper here. I'll just dump it on my paper. And we have a nice red copper solid here. And that came out of the coin right here. And here's a close-up of the end products. Coin has lost mass. Graphite is where the copper collected. Here's some of the copper solid with its distinctive color. Electrolyte solution over there, diluted with some water.